We are looking now at a problem for exam P on probability, also exam 1 of the Casualty Actuarial Society. But most of the time we know it as course P, the name given by the Society of Actuaries. This was posted by me on May 5th, 2007, and it has some new interesting question from a student. That's why I think it's a good idea to look at it. You have some information here about where you can buy the study manual for exam P that I wrote, also about our online seminars for the exam, and some practice, online practice exams that are adaptive that become harder as you get better. Here is the problem. You are given that the random variable x is exponential with mean 1, and that the random variable y is uniformly distributed on the unit interval from 0 to 1. You also know that x and y are independent. The question is to find the density of the joint distribution of u equal to xy and v equal to x over y. And there are 5 choices. And your first reaction should be, when you look at this, that this is a transformation, a two-dimensional transformation of a two-dimensional random vector into another two-dimensional random vector. You should have the formula for the density of the transformed random variable memorized. You should just automatically apply it. And that solution works in this case. There are some interesting complications that we will also discuss, but the basic method that you should know works. Remember that. So this is what we do. Because the two random variables are independent, the joint density of x and y is the product of marginal densities. So it's just e to the minus x times 1 for x positive and for y between 0 and 1. Because x is exponential with mean 1, and the density of exponential random variable with mean 1 is e to the minus x for x greater than 0. Y is uniform on the interval from 0 to 1, so the density of uniform random variable on the interval from 0 to 1 is just 1. It's always 1 over the length of the interval on which the random variable is uniform. And the length here is 1, so 1 over 1 is 1. In order to find the joint density of u and v, we need to first express x and y in terms of u and v. So we need to find the inverse of the transformation that we are considering. And that's the first step. Remember that. Note that all variables considered here, x, y, u, and v, are positive with probability 1. And u times v is equal to xy times x over y, because u is equal to xy and v is equal to x over y, so it's equal to x squared, so that you can write x equal to square root of u over v, because we know that x is positive with probability 1. And u divided by v is xy divided by x divided by y, or x times y to the negative 1, so it's y squared, and this gives y equal to the square root of u over v. So the inverse transformation in terms of the regular variables is regular variables instead of capital letters denoting random variables. We're writing just lowercase x, lowercase y to write the function, the two-dimensional function that we are considering. Xy is equal to square root of uv, so x is square root of uv and y is the square root of u over v. Okay, so given that we have this inverse transformation, we find its Jacobian, which is the determinant of the matrix of partial derivatives. So we need to take the partial derivative of x with respect to u, which is what? Well, x is equal to square root of uv. So the partial derivative of that with respect to u. Well, the derivative of a square root is 1 over two square roots, and then we multiply it by the derivative of uv with respect to u, which is just v. That's the first entry in that matrix that you see there in the left upper corner of the matrix. Then we take the partial of x with respect to v. Well, it's again 1 over 2 square roots, but now we take the derivative of uv with respect to v, which is just u. That's in the upper right corner of the matrix. Then we take the partial of y with respect to u, and y is the square root of u over v. So it's 1 over 2 square roots, the derivative of a square root, times, what's the derivative of u over v with respect to u? Well, it's 1 over v, or v to the negative 1. That's the left lower corner of the matrix. And then the derivative of square root of u over v with respect to v. That's 1 over 2 square roots. And then we have u over v, which is really u times v to the negative 1. So u stays there, and then v to the negative 1, the derivative of that with respect to v is minus v to the negative 2, and that's what you see in the right lower corner of the matrix. Then we take the determinant of that matrix, and we end up with, well, you multiply the left upper corner times the right lower corner minus the product of the other two entries in the matrix, and we end up with minus 1 over 2v. And the new joint density of u and v is the original density of xy evaluated at x that corresponds to u and v, and y that corresponds to u and v, times the absolute value of that Jacobian that we just calculated, which is going to be 1 over 2v without the minus sign, the absolute value. What was the original density that we had there? It was e to the minus x times 1. So it's just e to the minus x. And x is equal to square root of uv. So this ends up being e to the minus square root of uv divided by 2v. For what values? Well, x has to be positive, so square root of uv has to be positive, and y has to be between 0 and 1, so that the square root of u divided by v has to be between 0 and 1. That implies that u is positive, v is positive, and because u over v, the square root of it is less than 1, and they're both positive, then u over v is less than 1, which means that u is less than v. And that's all of the conditions. That's answer B, and we're done with this problem. But there is something interesting that we would like to discuss here that we will discuss in a moment. Now suppose that instead of the joint density of u and v, we want to find the marginal densities. I didn't give you this problem as an exercise for the exam, but a student asked, and it's an interesting question. And it's a bit too hard for the exam. But it's okay. It's a good teaching moment for me and a learning experience for you, I hope. So if we want to find the marginal density of u equal to xy, then we can do the calculation, the standard calculation of the marginal density. So we would take f sub u of u would be the integral over all possible values of v. And now remember that v has to be more than u. So it will be from u to plus infinity of the joint density that we just calculated, which is e to the minus square root of uv over 2v dv. That looks a bit complicated. So we try to simplify it by substituting. The most inconvenient part is that square root of uv. We call this x. Then dx over dv, the derivative is, well, 1 over 2 square roots times u. We did this calculation before, so this makes sense. When v is equal to u, actually x is also equal to u. And when v goes to infinity, x also goes to infinity. So we substitute everything. in this way, that we have e to the minus x over 2v. We'll leave this v for a moment there. And then dv is replaced by what? Well, if you take a look at this, if you solve the expression dx over dv equals u over 2 square roots of uv, if you solve this for dv, so we want to replace dv by something, then that something will be dx times 2 square roots of uv over u. And now the interesting thing is that we effectively have there square root of uv over uv, so it's really 1 over square root of uv, and square root of uv is x, and the 2 up and down cancels. So we end up with the integral from u to plus infinity of e to the minus x over x dx. And I'm sorry, that's the best we can do. There is no really better way to express this density. That's what it is. It will be given in this integral form. For the calculation of the marginality of v equal to x over y, we have f sub v of v, well, again, over all possible values of u, integral of the joint density. But since v is bigger than u, that means that we do the integral from 0 to v of e to the minus square root of uv over 2v du. And then again we do a substitution. This time let's call it z equals square root of uv. Then dz over du is 1 over 2 square roots of uv times v. And when u is equal to v, z is equal to v. And when u is equal to 0, z is equal to 0. So now we have the integral from 0 to v of e to the minus z dz over 2v times z. A bit complicated, but we can put that 1 over 2v squared in front, and then it becomes the integral from 0 to v of z e to the minus z dz. This is actually an integral of a density of a gamma distribution, which is the sum of two exponentials. So it's really the CDF of that gamma distribution, but I do not assume that you have memorized that. So we'll do integration by parts in this integral to simplify it a bit. We take the first function to be z and call it s, then ds is dz. And the second function we call it t, and it's equal to e to the minus z. Then dt is e to the minus z dz. And what we have is the integral of z times e to the minus z dz, or s times dt. And that, by integration by parts, is equal to, well, the integral of the products, I'm sorry, the product of the two functions at the top, not the integral of them, evaluated from 0 to v. So z times e to the minus e to the minus z. And then minus, but it's a minus minus because there's a minus in front of e to the minus z2. So plus integral from 0 to v of e to the minus z dz. That's much easier because you know that that's the integral of the density of exponential distribution with mean 1. So you can immediately say, well, this is going to be the value of the CDF, cumulative distribution function, of that exponential. So what we get is 1 over 2v squared times minus v times e to the minus v plus 0 plus 1 minus e to the minus v. That last part, 1 minus e to the minus v, is exactly the CDF of exponential with mean 1. So we get the answer. It's a lovely answer. 1 over 2v squared times, in parentheses, 1 minus e to the minus v times e to the minus v for positive v. So this is what we have. We found those marginal densities, not very nice looking. And it's tempting to see if we can get something nicer, a better answer, using an intuition inspired by what we've learned about convolution method. If the probability density function of the distribution of a sum of independent random variables x and y is established by the convolution formula that you see here, can't we calculate the probability density function of a distribution of the product of independent random variables x and y using the same intuition? And I'm sorry, but the answer is no. And this is an important warning, because intuition is a great thing, but in mathematics you have to be very careful. Sometimes it can be misleading. And in order to see how it's misleading here, we need to understand first where the formula, the convolution formula, where it comes from. And once we know that, we'll do the same thing for the formula for the product, for the density of a product, and you'll see what that formula is. It's technically not on the exam, at least not to my knowledge, although the more you learn, the better. So maybe you'll get a problem like that and you'll just do it instantly thanks to knowing the formula. But just seeing the formula will be good for you. Okay. So we actually know where the convolution comes from, where the formula comes from, if we look at the cumulative distribution function for a sum of two independent random variables. Well, the CDF is the probability that x plus y is less than or equal to something. They'll call that something S for a sum. And how do we calculate that two-dimensional probability? By taking the integral of the joint density over the region where x plus y is less than or equal to S. So if x runs from minus infinity to plus infinity, y is constrained here. Y has to be less than or equal to minus x plus s, or s minus x, which is what you get when you move x to the other side of the inequality under the probability. So this is the double integral for x running from minus infinity to plus infinity, and y running from minus infinity to s minus x, because y is less than or equal to s minus x, of the joint density, because that's how you calculate probabilities for continuous random variables. You take integrals of the density. Okay, well then, we do the calculation of that integral from minus infinity to s minus x of the density of y dy. And then once we do this, we take the integral from minus infinity to plus infinity of f sub x of x dx times what we get here. But what we get here is simply the cumulative distribution function of y evaluated at s minus x. Well then, the density is the derivative of the cumulative distribution function. So we take the derivative of this, and you know from theorem Henri Lebesgue, a great French mathematician, proved that the derivative of the integral is integral of a derivative. So you can move the derivative inside. And what's the derivative of f sub y of s minus x? Well, it's the derivative of big F, which is little f, but then there's a function inside, which is s minus x. What's the derivative of that? With respect to s, it's 1. So what we end up with is the integral from minus infinity to plus infinity of f sub y of s minus x times f sub x of x dx. And that's your standard convolution formula. It's very nice, very intuitive, a great thing, useful on the exam. You should know this for the exam. So now let us apply the reasoning carefully to a product of two independent random variables, with a product of two random variables called u equal to xy, as we called it in this exercise. So we have f sub x times y of u, that's a cumulative distribution function of a product, is simply the probability that x times y is less than or equal to u, which, again, we do the same thing. We let x run freely from minus infinity to plus infinity, and then y is constrained to be less than or equal to u over x, so it runs from minus infinity to u over x. And then we take the integral of the density to get the probability. And again, we look at the part with y only now. And so we do the integral from minus infinity to u over x of f sub y of y dy. And that's, of course, the cumulative distribution function f sub big F sub y of u over x. Great. So then we take the derivative of that to get the probability density function, the density f sub x times y of u, is the derivative of that. Okay, well, that's the derivative with respect to u of that integral of big F times little f, big F of u over x. We move the derivative inside, and we take the derivative with respect to u. U is only in the big F sub y of u over x, so that's what we take the derivative of. The derivative of big F is little f sub y of u over x. And then there is an inside function of u over x. What's the derivative of that with respect to u? 1 over x. So we end up saying that this is equal to the integral from minus infinity to plus infinity of 1 over x times f sub y of u of x times f sub x of x dx. So it's a different formula. It has 1 over x in it. That 1 over x came from a derivative that we were taking of the cumulative distribution function evaluated at u over x before we were evaluating it at s minus x with respect to s, and that derivative was 1 and it didn't affect anything. But now the derivative affects things. It's a fair warning. It's very intuitive. The intuition of convolution is so nice, it seems that, oh, you just added up all the probabilities of all the possible combinations and everything works. And it's okay if you have that intuition, as long as you understand its origin. It's a bit more complicated, and sometimes intuition in mathematics can be misleading, so you need to be careful. And the most wonderful and really stunning example of intuition being just knocked out and left unconscious by mathematics is the Banach-Tarski paradox. Look it up on Wikipedia. An amazing story. If you find time, study the proof of the Banach-Tarski paradox. It's an incredible exercise. You might spend a long time with it, but it's very enjoyable. So good luck in your studies, and thank you very much.